In this video, I discuss the motion of a charged particle in a uniform magnetic field. And the special case that I am assuming in this video is that the angle between the velocity of the positive charge and the magnetic field is 90 degrees. It's just a special case, and this makes our calculations a little simpler. And after we understand the special case, we will understand the general case when the angle is not 90 degrees. As seen in the picture, the magnetic field is pointing into the screen shown by crosses, and the symbol for the magnetic field is represented by B subscript IN. Then the positive charge of mass M moves with the speed V and makes 90 degrees angle to the magnetic field, as we discussed. And if all this gets satisfied, then the path of the positive charge inside the magnetic field is a uniform circular motion. And the radius of the circular motion is given by R equals to mv divided by qb. This is the equation for getting R. Now, if V is not perpendicular to the magnetic field, then the charge will not undergo a uniform circular motion as shown. Instead, it will take a spiral path. And in the same formula, the velocity should get replaced by the perpendicular component of velocity, which is perpendicular to the magnetic field. So in this, R is the radius of this uniform circular motion, V is the speed of the charged particle, and F is the Lorentz force experienced by it. B is the magnetic field, which in the picture is shown using B subscript IN. So this formula gives the path of a uniform circular motion taken by a positive charge that makes an angle of 90 degrees with the magnetic field. Let us do a problem that uses the formula mentioned in the previous slide. Calculate the radius of curvature of the path of an electron having a velocity of 6 times 10 to the power of 7 meters per second, which is perpendicular to the magnetic field strength B equals to 0.5 Tesla. So this is a fairly commonly observed numbers. If we were to look at something called a cathode ray tube, which was popular in older times, computer screens and televisions. So if you were to put a magnet on the computer screen, this magnetic field produces a change in the path of the electrons that travel inside the vacuum tube. And using the formula that we developed, whenever the velocity of the charged particle is perpendicular to the magnetic field, the path is a uniform circular motion with R given by this formula, and we just substitute for mass of the electron times the velocity of the electron times the charge of the electron here. It's a negative charge, but in the formula we just use positive values because radius of the circular path cannot be negative. And then finally the magnetic field given by 0.5 Tesla, and then this gives us the radius of curvature of the path taken by the negative charges, which comes out to be 0.68 millimeters.